Hi everybody, my name is Austin,
My name is Stephanie.
and our project is on the prevention of thermal failure for the WALI PEP-GS mission.
Just a quick disclaimer before we start. We are students here at Western, and this is for a curriculum requirement. So if you do choose to use any of this, please do so at your own risk.
Just some acknowledgements before we get started. We would like to take a moment to recognize and thank the following parties. CNR Tech, first of all, for providing us with the multiple student licenses for Thermal Desktop. That is the software that we used to perform this analysis. We would also like to thank Dr. Christina Lemmer for her knowledge throughout this project, but also for allowing us to be a part of WALI, which is a fantastic organization that we have enjoyed throughout the years. And finally, Mr. Brendan Schultz for sharing his time and knowledge with us as we dove into the world of thermal engineering.
So our project is for WALI, Western Aerospace Launch Initiative, and their mission, the performance of electrospray propulsion on ground and in space, otherwise known as the PEP-GS mission. So electrospray propulsion is a relatively new type of propulsion where step voltage is run across an electrode extractor, and that emits the liquid propellant, which is the fuel for the satellite. However, we will not be focusing on the electrospray tester, as our project is based off of the thermal analysis of the components that are inside the satellite. So in order to determine success for our project, we are deciding that all components that we have need to survive within a certain temperature and need to operate at all times during the mission. A secondary objective that we have, however, is that we would like to keep the runtime of the simulation fairly low because we do not want to be waiting days for the simulation to run.
So just a little bit of background on thermal analysis. Heat transfer in space is notoriously complicated due to the lack of atmosphere. You can't just attach a fan to your satellite if it gets too hot and expect it to cool off. Only heat transfer that occurs in space would be radiation from external bodies to your satellite, radiation from your satellite into outer space, or conduction throughout the satellite itself. So the first step in order to determine whether or not the internal components will survive is to create a thermal model and then to run an analysis on that thermal model. If success is not achieved, you need to implement thermal control. And thermal control falls into two categories, active or passive. Passive thermal control is defined by anything that does not turn on or off when a threshold is reached. It would be something like thermal strapping, where you attach a piece of conductive material to 2 points on a satellite, and that will allow conduction to occur more easily and flow from higher temperature to lower temperature. Active thermal control, on the other hand, is something that will either turn on or off if the threshold is reached. For example, a battery heater will turn on if the batteries get too cold and prevent batteries from freezing.
So for our thermal budget, we have the different subsystems, and each subsystem has their own component. Each component has a range of survivable temperature and a range of operational temperatures. In order to have a successful mission for the if there's thermal failure, if any of these components go outside of these ranges. Our goal is to keep everything within the operable range and not just the survivability range. However, if it doesn't need to work, we can also do power loads to make sure that it can heat up as batteries were suggested earlier. For our getting introductory to Thermal Desktop, we started with a one node 100mm brick, which is shown here. And this is really just to figure out how to define material properties, the orbit that we were going to use, and we ended up deciding on using the orbit that the ISS space station is on, and also to define the case sets of the orbit and the materials. So here we made it out of an aluminum brick, and we'll explain why it doesn't exactly work as well as we thought. So the range for the thermal one node model was from about 97 to 150 degrees Celsius, which is very warm. That is quite hot for what we were expecting. However, it's because it was a thermal brick, and with the solid material, it holds heat better than another model with a shell would be. So this is not very accurate. However, it was a starting point for us for working with thermal desktop.
After our one node analysis, we moved on to a 22 node analysis. The 22 nodes were selected based on the geometry of our satellite. We are using what is known as a 6U satellite, U meaning units. One unit is approximately 100 millimeters by 100 millimeters by 100 millimeters. So this 6U satellite will be approximately 300 by 200 by 100. So each node is about 100 millimeters by 100 millimeters, with 6 nodes on the top, 6 on the bottom, 3 in the front, 3 in the back, 2 on the left, 2 on the right, leading us to 22 nodes. While this model more closely represented the geometry of our satellite, it still lacked the internal components. So we only completed this analysis to get a better idea of what our range should be. But we did implement the use of thermal shells as opposed to thermal solids. This allowed us to A, cut down on the runtime, B, cut down on the amount of material. The results from which are right here. Our range is from about 0 degrees Celsius to 28 degrees Celsius, which was a much better temperature range. If our internal components ranged from 0 to 28, we would be very happy. However, they were not modeled yet, and so that would be our next step.
So for a summary from the 1 and 22 node analysis, we found that having more nodes creates a more accurate simulation. So therefore, going forward, we're going to use as many nodes as we can, especially in areas such as the structure that see a really large heat flux. We also concluded that thermal shells reduce runtime, which is important. And so therefore, whenever possible, we are going to use thermal shells rather than thermal solids. And also, we had a high conduction throughout the physical structure, and that definitely increased the accuracy of the model.
All right, so this is an image of our final model as it stands right now. I say as it stands right now because the WALI PEP-GS mission is still in the design phase, so there may be changes that occur later down the line. This is why it was important for us to have such a low runtime, because if we needed to wait multiple hours to get a result back, if our structures team decided to change the internal layout, we didn't want to have to wait that long to get our results. So breaking down the model, we have over 150 nodes, most of which lies in the structure. We have the heat loads on the internal components being represented as their power draw. So for example, if our onboard computer uses 1 watt of power, it will have a heat load to represent that power draw as 100% being converted into heat. While this is not a perfectly accurate representation, it is a much better representation than having no power draw being converted into heat. We also had it color coordinated mostly by subsystem.
First subsystem we're going to get to is the main structure, which is modeled here in gray, and this was modeled out of aluminum. And then you also have the secondary connectors modeled here in pink. And something very important for the structure is us modeling it as a bracketed instead of just having them float over each other. We modeled it as them being bracketed together, which would be more accurate based off of the final model when it gets into building stages. So the structures system has the most nodes in our entire model because it will allow for better conduction. And another thing to note is that here in green are PCBs, otherwise known as printed circuit boards. And these are not necessarily something specific to structures. These are specific to all subsystems and are needed for the satellite to run. And here's the overall data. As you can see, it ranges from about a little bit less than -10 to around 65 degrees Celsius. We are not going to assume that the structure is going to fail during this mission, because if the structure fails, then all of the other components will have already failed, meaning that the mission will be unsuccessful. So therefore, we are assuming that the structure is not going to fail during this mission.
Moving on to the next subsystem, we have Command and Data Handling, or CDH. Their onboard computer system is modeled here in purple. Onboard computer system is the only component we have from them thus far. It is modeled as a thermal shell using PCB properties, which is then connected to another PCB and then connected to the structure. The analysis shows that the onboard computer will range from about -10 degrees Celsius to 55 degrees Celsius. This is good because the operable range given from the datasheet is from -40 degrees Celsius to +60 degrees Celsius. This is close to the higher end of the operational scale, but it is still within the operational range. So that means our onboard computer system will be able to be active at all times, which is good because that's what we need.
Next is communications, which is shown here in orange. So communications has two different components, which are the antenna and the transceiver. The transceiver is modeled as a PCB, whereas the antenna is modeled as a copper antenna prong. So for the models, the transceiver is modeled as a thermal flat shell, and the antenna is modeled as cylindrical shells. For the data, the antenna ends up falling between -3 and 48 degrees Celsius, which is in the acceptable operable range, which is -30 to 65 degrees Celsius. And then the transceiver ranges from between 5 degrees Celsius and 7 degrees Celsius, which again falls in within the operable range of -40 degrees Celsius to 70 degrees Celsius. Therefore, both the components for communications fell well within operable range.
Moving on to the next subsystem, we have Guidance, Navigation, and Control, or GNC. Their subsystem is modeled here in blue. GNC has a multitude of components, but the most sensitive one would be the reaction wheels. Most of the components were modeled using aluminum properties, although some of the electrical components were modeled as PCBs. So the results from the GNC subsystem show almost no variation between components, ranging between 0 degrees Celsius and 55 degrees Celsius. Since the reaction wheels were the most sensitive, with an operable range of -10 degrees Celsius to 60 degrees Celsius, they fall within their operable range. And since the reaction wheels can operate at all times, so can the rest of them.
For the payload, the component for that is the Electrospray Propulsion. However, that has not been decided yet for the mission, and we do not have much information on it at this time. For the model, however, we modeled it out of aluminum, and it is shown here in red. Even though we don't have much information on it, we still modeled it and ran it, and that model ended up being around 0 to 45 degrees Celsius. And even though we have not decided, it has not been decided what electrospray thruster is going to be used, we communicated with the payload team lead, and it had been decided that that range would be acceptable. And then to follow up, we also cross-referenced the Electrospray datasheets that are online to confirm that these ranges are adequate.
Moving on to the final subsystem, the Power Subsystem. Power is modeled in two different colors, yellow for the solar cells and light green for the internal components. The solar cells have been given solar cell properties as defined by Thermal Desktop, and the internal components are mostly modeled using PCB properties. So the batteries are the most crucial component and the most sensitive component in the Power Subsystem. And their temperatures range from 2 degrees to about 46 degrees Celsius, with their acceptable range being from -30 to +60. That is their operable range. Note that the temperature that we modeled refers to the outer shell of the battery pack. The batteries themselves will have active thermal control in the form of battery heaters, which will keep the batteries from freezing if that temperature does indeed get too low. However, as modeled, they will be able to operate them. For the solar cells, The analysis showed that they will range from about negative 15 degrees Celsius to 67 degrees Celsius, with the acceptable range being negative 40 degrees Celsius to 80 degrees Celsius. So there is a wide swing in temperature being modeled, but they will be able to withstand it since they are fairly sturdy.
Here are some properties that were used from Thermal Desktop. So these are the properties when we refer to something as being made out of aluminum or copper. These are the properties that Thermal Desktop uses to calculate our simulations and does the numerical methods for that. So overall, it has been deemed that all of the components are capable to be in operation at all times during the mission. And this was made accurate because of how many nodes we had on our structure system. The total runtime for the simulation is about around 30 seconds, and that's very good. So that way we didn't have to wait hours. And then it is determined that the WALI PEP-GS mission will not experience thermal failure. Any questions?
Back to the so it looks like you only have solar cells covering less than half of the satellite. Is that just for imagery, or is that how?
That is how it was modeled. As of right now, or at the time that we made this model, the power team said that those two faces would be the most likely to have solar cells on them, and the rest were still being decided at the time. So if we need to, we can copy those solar cells and move them onto the other faces. But as of right now, those are the only two faces that have solar cells.
The addition of those other faces affect the model.
If anything, I think they will likely reduce the temperature of the overall model, but I don't think it will affect it enough to make anything go outside of its.
Why would it reduce? Why would it reduce?
Because I think most of that heat would get absorbed by the solar cell, and there would be, since the solar cells have the greatest range in terms of negative, most of the heat would flow to those solar cells. Question? Where? Oh, okay.
So you said that none of the systems were experiencing thermal failure. That was low. PLC was about 5 degrees off. Would you still consider thermal control in that close?
In the event that it is that close moving forwards, yes.
But we don't have the final design yet, so this is just the basis, and therefore it's more consider a thermal failure with the final design. It's
Yes. Is there any particular reason? Mostly just because they were readily accessible in Thermal Desktop, and it's very easy to say that an electrical component can just be circuit board because it'll have very similar makeup in terms of the system. Question? Share with us what we tried to do.
I think the most challenging was the difference in designs. Like this isn't the final model, so trying to model something that isn't final was very hard, and everything was changing, and you had to communicate around all of the different subsystems with all of their different components as well.
In addition to that, I would say learning how to use all the different technology, but it is not an easy software to work with, although with the help of hey, we can